Let us try to understand the gated self-attentions by using a very simple example. So in this example, I will consider a binary sentiment classification task with positive and negative sentiment, and the sentence is a little sarcastic. The phone looks gorgeous and felt premium, but constant crashes and poor battery life made it unusable. So, due to the presence of those crashes and unusable, it shows that it actually has a negative sentiment. Here, the vanilla sentiments confuses a lot. So, we will try to understand that how gated self-attentions makes the difference. The first important question is for gated self-attention is how many gate you will put here. Here we have just a binary sentiment classification task. So one gate may handle everything. So in that case, we can use the prior. For example, generally in the case of embedding, sentence embedding or text embedding, we use the tokens like CLS and SEP at the end of sentence and CLS as a prior or at the starting of the sentence. We will use gate for CLS prior for sentiment classification. So we will have one gate in this case, and this will help us to simply understand the how it works. So first we will take the input sentence, then we will calculate the token embeddings, and after that we add the prior CLS token and you calculate its embedding. So once we have all those available, we will apply the simple process to compute the vanilla self-attentions. So this process is very simple. How to calculate the vanilla self-attentions for any given data? You can watch my previous tutorials. So in this case, as we have a prior CLS, so we will use XCLS as a query, and then we will calculate the attention score and context vector score for prior CLS with respect to the all words of the text. So after the end of this, we will have vanilla self-attention score like a context vector score for prior CLS with respect to all words in the sentence. Now the role of gating mechanism starts. So gating mechanism is achieved by using some multi-layer perceptron. It may be single multi-layer perceptron for a very simple architecture. So you already know that all multi-layer perceptron generally contains two different parts, summation parts and non-linear parts. So non-linear parts we achieve through, here we use sigmoid functions for non-linearity. So in the summation parts, we use two things. First, embedding XLS, and second is weighted gate matrix, so WG. And then we use the XCLS, that is embedding, and plus bias if they are available. And we put XCLS is coming from here, we design WG here, some bias we fix here, and we pass all those things to here, and then we get output in the range of 0 to 1. So now we will use the importance computed here for the gate to decide whether we have to what amount of importance we have to give to the vanilla self-attentions for the CLS token coming from here, or what amount of importance we have to give the actual embedding score for XCLS token, so that we decide with the help of gating mechanism. So suppose how we decide, we take G element wise multiplications. Suppose this is vanilla self-attention score or context vector score of XCLS is A. So and then we make 1 minus G into XCLS. Why XCLS? So here we decide that if score of G is very less, suppose it is 0.2, this means we are giving just 20% importance to this attention score coming from here. And suppose, and in this case we are giving 80% importance to the uh, embedding score of XCLS, and then we combinedly calculate the gated attention score for CLS token, and we will use this information in computing the classification task. So this is the process. So this is for one single token. Now let us try to understand the generalized case. For example, suppose you are calculating POS parts of a speech for each of the token, or you are computing named entity recognizer or preparing named entity recognizer, so named entity for each of those tokens. So in that case you have to put the gate for each of those tokens, only then you will get such kind of scores. So in that case we define the gated attention score for each of the tokens like x hat I equal to gi, means gate for the token xi, gated score for calculated for token ai, gi, and gated attention, and the attention score, vanilla attention score calculated for token xi, and then 1 minus g into 1 minus g element wise multiplications xi, so embedding score of token xi. So this is the way we calculate the gated attention output for a given token. And you are already aware of this, how the gating function, that MLP system is actually working here. So this is the process. Now we will go through a very simple example and try to achieve that, how it actually works. So task is same, sentiment classification, but here the changes that we made, we are just considering few important tokens like gorgeous, premium, crashes, and unusable in entire computations. Just for simplicity, this is not an authorized computations. I have just used those words and some computations to showcase how the computations or flow is actually working. So first take the XCLS. Suppose this is given 0.6 minus 0.4 for gorgeous, premium, crashes. These are the embedding scores. All are 2D embedding scores. Query Q, and we reuse the XCLS, but we flip the sign of second slot to make the similarity and favor the positive words. So we are just trying that if we change the sign, then how it behaves. In this case we have dimension, embedding dimension 2. So our this gating mechanism, the multi-layer perceptron which are used for gating, and the weight matrix for this gate WG will have 2 into 2 size, and suppose we consider it here like a -1, 0, 0. Please note that all these calculations are just to demonstrate how the gating mechanisms are working. Suppose we take bias equal to 0. So now we have to calculate the vanilla self attention for CLS token. So we will consider CLS as query, and then we will calculate the dot product, then we will calculate the softmax, and then we will calculate the context vector score for vanilla for CLS token. So till here it is very simple. So this is the dot product. So dot product is like Q into Xi. So these are actually our, so Q is actually CLS token. So for CLS token you already know that these are the embedding points, and for gorgeous it is 0.8, 0.9. So here you can see that 0.8 is used here, 0.9 used here, 0.4, 0.6. So 0.4 is here, 0.6 is here, 0.4 is here. So like that. Similarly 0.6, 0.4, and these are embeddings coming for premium, these are embeddings coming for crash, these are embedding coming from usable, like that, and based on that we will get the dead dot product. After that we calculate the softmax weight. So first we calculate the exponential of each of those numbers. So these are the exponential of each of those numbers, calculate the sum of that, and then we take the exponential divided by sum of exponentials, and that this way we get the softmax score for everything. So once we get the softmax score for everything, so we have alpha I means alpha 1, alpha 2, alpha 3, alpha 4, like that, and then we calculate the context vector score, which is alpha I into xi, alpha 1 into context vector score x component here. So if you see the gorgeous, it is embedding is like 0.8, 0.9, like this, 0.7, 0.8. So it is like this. So same is here. So 0.8, 0.34 into 0.7, like that it is calculated. So first part x component, which is calculated here, decides that how much importance of those words are in the text, and y components are giving that how much importance of those words in deciding the sentiment. So here the score positive indicates that we are going into the wrong directions. So now we will start with this way of calculations, means we will apply the gating mechanism. Till now we are here without gating, this is the situation, and now we will apply this gating score. So when you apply the gating score, you will find that for these computations WG, the initially we had decided WG as -1, -1, 0, 0. So it is here, and then XCLS we had 0.6 and 0.4, and bias is equal to 0. So based on that we get this gating score. Now we have vanilla and XCLS both, and gating score that is available here. So what is our vanilla computations? So x component is 0.641, y component is 0.349. So for x component we will calculate the gating score. So G 0.354, 0.354, vanilla attention score is 0.641, so it is 0.641. Again 1 minus G is 1 minus 0.354, this will be 0.646. Now this is XCLS, so XCLS value x part is 0.6. Similarly y component will be computed, this part here, and then this part is calculated here, 0.349. So it is 0.349, we took the same value, and 1 minus 0.354, like this is 0.646, and then this score that was actually given earlier here. So we just apply it here, and then we get some negative sentiment here. And here also again the x component is for to get that how much importance of those words for the given text, and y component shows that what is the importance of those text, or for sentiment, means how much it goes towards the sentiment. So this is negative, means we are going into the right directions. So here you can see that it is completely flipped, means positive to negative. So why this flipped happened? Because in vanilla we just take the computation sum and we ignore the CLS prior. So we are just ignoring this part, And then in final sentiment, that's why the final sentiment sign is wrong. And in other case, we are considering the prior also, because why we are considering the prior, because this score is high and our attention is giving just 35% weightage and 65% weightage is coming from the prior, means 65% score is coming from here, only 35% score is coming from here. So when we combine this, it automatically changed the sign. So that's why this flip happened. And that this is the process of getting system is actually working. So now you will ask questions that in the current scenario we had just two dimensions. Suppose we have a dimensions like 1024, then what will happen? So in this case, getting matrix will have dimensions of 1024 into 1024. So if you calculate the parameter 1024 into, so this will be the total parameter size, and B bias will also have 1024. So total learnable parameter will be like this. This is too high in number. So in that case, what happens? We generally take two layer perceptrons. Means this is one layer perceptron, and again we apply another perceptron as a hidden layer, and then so in this case what happened here, weight matrix will become, suppose here we take a second layer perceptron having size 128, so it is like 128 into 1024 and 1024 into 128, so it becomes like that. So in this case totally reduces 4 times with respect to the current things. So this is another way. There may be multiple other ways to control this. Another things are like how many gates are required. So I already said for classification, binary classification, we used one gate for the CLS token. Suppose for token classification like NER and POS, then we will have total number of words in the text is K and one CLS and one SEP, then there will be K plus 2 gates will be required. Again for sequence to sequence and language modeling, how many gates are required? So it will depend upon two different things. First is based on the time steps or based on the decoder position. Again attention over memory blocks, it depends upon two different things. It depends upon like gate control flow across the multiple outputs. It doesn't depend upon token.